Hello, welcome to DSC conference. Our next speaker is Mike Kollo, Forecasting Free Will, AI and Ethics in the Next Decade. To use of data to infer future likely actions among agents, citizen, and system begets, questions of causality, free will, and will often run into challenges from our inherent mental models. So while these models are developed and almost daily in our society, deeper questions as to what they enter after elements of our society about own actions and behaviors, and more importantly, the outcome that they create when deployed at scale is a developing area of AI governance, so also referred to AI ethics. So Mike, it's your time.
Hi, everybody. My name is Michael Kollo, and I am from Fathom.ai, a strategic workforce tool. Today, we'll be talking a little bit about ethics and AI, and specifically around bias and the kinds of things that algorithms, I suppose, are telling us about the world and about people. It's going to be quite a quick presentation that is essentially won't do any justice to the huge topic that is ethics and AI. What I'm hoping to do is to spark your interest in this area, to get you thinking about some of these issues that are around about algorithms and AI, and really to kind of make you think about, especially if you're designing these algorithms, what your role is in all of this. So let's get going. At the beginning of every good presentation is a good quote. So we're going to fly through this presentation at skill, and every time we're going to stop a little bit and learn a little bit more about some particular element. But I wanted to start with this particular quote, which is when we're thinking about how algorithms think or how algorithms reason, I suppose we may as well start thinking about how people reason and how your mind reasons in terms of what is logically. The mysteries that surrounds a thinking machine really are the same mysteries that surround a thinking man. So, firstly, I think when we think about algorithms in society, we have a lot of horror stories that we are presented with around this idea of a highly empowered algorithm that knows everything about us, that is trying to manipulate us, trying to harm us, trying to control us in very different ways. I think the truth is a lot more subtle than that and probably a lot harder to put your finger on. A series of algorithms that governs increasingly decision making in our society is really about a series of decision agents that are encompassing some amount of logic in the way that they process uncertainty, the way that they process information. And essentially, no one agent or no one algorithm need be a particular problem, but it is the combination and is, I suppose, the scalability of these algorithms that presents the challenges and some of the unforeseen errors and unforeseen outcomes that might happen, some of which we'll kind of touch on today, but won't really get into it. So I think the idea that an individual algorithm becomes a scale solution and then kind of takes over the world is not really reasonable. I think that we start to think about a certain way of understanding the world, and through that way, a network effect becomes very pronounced through a series of algorithms, I think is much more likely, and perhaps the way we should be thinking about these kinds of problems. I think maybe a good thing to start with is that algorithms are not moral agents. They do not have intent. They represent people's intent. They represent people's logic. So if you're somebody who writes an algorithm down and then you go and execute it and put it into the world, it is your will manifesting itself, even if you may not have thought about a conscious decision about how you characterize people for credit cards or how you determine whether someone is going to commit a criminal activity. It is in fact representing your mindset or your will. And that's something we're going to return to a little bit later, but it's important to begin with. What are some of the more common examples when I'm talking about algorithms in the context of today's presentation? I'm really thinking about decisions about people with uncertain outcomes. So as an example, you might have a policing prediction tool, which is very common for crime and criminal activity. These algorithms essentially take information about people or about location and create probabilities that somebody is going to commit a crime, someone's going to commit a crime again, that some area of a city will need police protection and so on. They typically take data of historic criminal activity and then they go and apply it to the area, which has all kinds of interesting problems attached to it. The second kind of use case is quite common as well for hiring. So if you're looking at determining whether somebody is suitable for your job, but you have a lot of applicants, you might decide to feed through all these applications into an algorithm. The algorithms will decide based upon different kinds of characteristics, what to pick out for potentially interesting candidates. Again, a kind of scalable solution, but importantly, you can't lose track of what it's actually trying to do. So even if, for example, you don't allow an algorithm to learn about the sex explicitly, about male or female applicants, and therefore for you to be biased, it can subtly pick up words that men are more likely to use than women. In this case, a famous example when men use the word execute a lot more in their CV applications into Amazon than women did. Finally, reinforcement beliefs. This is a really interesting example and probably a really big one that we won't have time to cover here. But this is the idea that if you put an algorithm into the world that is a source of truth, as to, for example, what determines good credit rating or what determines, let's say, intelligence or future academic performance, that you have an impact on society. Not only the fact that people tend to game that system and to rely upon that stuff, but they tend to start to believe it, even if it's nonsensical. And this is a classic example of blue and brown eyes experiment that was done in the 1960s, which was around an experiment to see whether you could make people believe that the color of the eyes was determinant of intelligence. Turns out you can without too much effort. So you can imagine what an algorithm could do on a mass scale for a society. What is our aim in creating equal, I suppose, algorithms or ethical algorithms in our society is typically to gain equality of opportunity. So what we're trying to do is we're trying to create algorithms that evaluate opportunity equally across different groups of individuals, even if the outcomes of those decisions may be quite different. So we want to give equal opportunity for people to become nurses, but at the same time realize that in society, many more women choose to be nurses than men. And if we for a moment think that that's a decision around free will or preference, that's okay, so long as we've given people equal opportunity. So I'm going to take you through a bunch of really, really quick case studies, but these are so quick that we're going to fly through them. Imagine you have a standard model. You're trying to forecast something in Y. Let's say, for example, someone's credit rating, their probability of repaying, or so their maybe their choice of a career or something like that. You've got a bunch of really nice variables X that are really genuinely determining Y. You've got a bunch of weak variables which are not very good, which are B. You've got a functional form in F. And then you've got a whole bunch of protected variables that you're trying to be very careful with, things like age, race, gender, and so on. You've got some free will, you've got some error in there, and you're like, okay, great, let's go for it. So a typical setup, as an example, is you would take a fairly set of data, some of which will be real determinants like X, some of it will be weak determinants like B. You put it into a particular framework, whether that's a simple OLS regression or whether that's a highly nonlinear deep learning model, and you go and train it on a particular piece of data to see which determinants are driving what. And what you're really doing there is you're saying, here's my determinants together plus an error term equals my data set. So my expected outcome essentially is my model. And whether you're trying to think about the probability of credit repayment, which is some future action that somebody will take or not take, or whether you're thinking about future career choice, typically these models are based upon those type of frameworks. So what does it mean when you have biases? So a typical proof or typical check of bias will be to take the output of a system like that and to check, as an example, whether the probability of repayments varies across your protected variable Z. So in this particular case, gender. So men have a higher probability of repayment than women. You would say, well, that's a problem. We have a biased algorithm. So you would say solution one. Solution one is don't use gender as part of the model. So typically models will say, well, we don't use gender, we don't use race, and therefore we're not going to make decisions based upon those characteristics. That's great. But of course, you can use many variables in your model that are correlated to Z. So even though you're not directly using it, your model is tilting into other variables that are using it. And what's really important to understand is that in your data sampling, you are not facing off against an unbiased world. So the world is biased, therefore you are, let's say, receiving, in this case, more men have repaid in the past more than women have for whatever reason, but you don't have a full data set where you have all permutations and therefore equality. So you're having to try to carve that out. So in this particular case, X is related to your variable Z. So what do you have to do? You have to try and normalize X's. So you're going to normalize X to Z, you're going to normalize Y to Z. And that's statistically a great result. But of course, what happens is you start to lose intuition, you start to lose any acceptability around this. And in fact, you actually can come up with really bad adverse outcomes where you're essentially subsidizing one element for another. So, as an example, in the previous case, if it's true that we've on average had worse credit for women than for men in our sample, that might mean that if I then normalize my variables, if I create a subsidization effect, essentially, that I start to subsidize something that I shouldn't be in the case of worse credit outcomes. A classic another example is where B is related to my protective variables. So these are weak variables that I have in my model. I might have them there because I've got no good X variables or because I'm exploring different kinds of alternative data sets. I'm using postcodes, I'm using special keywords, I'm using some natural language processing. But in all of these cases, B is a very weak proxy for really what I'm trying to express in the future. A typical example today, we'll be talking a little bit about ethics and AI and specifically around bias, but it does mean very, very different things as an example. So what that tends to happen is if I feed that into my algorithm might decide that actually I'm going to create a whole different model for different races or races that they will try to use social media information to inform future credit rating. And of course, what they were trying to do is they were trying to use it as a weak form of B to predict it. But in fact, what ended up predicting is again certain gender bias and other types of elements in terms of what the correlation looks like. Another kind of bias is where the error term is related to Z. That's a very typical kind of heteroscedasticity problem from econometrics for those of you that ever want to look that up. But it's really related to the kind of error bounds or the way the error function behaves relative to Z as well. Finally, you might have a really interesting problem where, again, I intonated to this before, you have a selection bias. Selection bias means that you are just drawing certain types of, from a certain distribution that is favoring differently across different groups of protected variables Zs. And so there's actually a lot more subtlety to this effect than just simply levels. It may well mean that you simply don't have enough of those types or variety of those types of data points and their gender or that race and so on. And so therefore your model is having to fill in. So as an example, if I'm trying to provide credit for a whole population, I may not have, let's say, African American women above age 65 very well represented. So my model is having to fill in for those characteristics, and therefore I'm not really very good at that element relative to other parts of the workforce or other parts of my data population. That's a form, I suppose, of bias, but it does mean very, very different things as an example. So what that then tends to happen is if I feed that into my algorithm might decide that actually I'm going to create a whole different model for different races or genders as subsets and different determinants for those because it's a deep learning system because it can do what it wants. So essentially what it will do is it will take that data and say, well, for this cohort of people, I'm going to use these data sets because I have them available. So for women, I've got a lot more data available on shopping trends, for example. So I'm going to use a lot more shopping information to determine whether women are more credit worthy or not. And for men, I have a lot more, let's say, sort of a fitness data, or I have more location data, or whatever else I have, and I'm going to use that kind of data for men. So essentially leans into what it has and what it knows about those two groups, and it almost kind of creates two separate models. And in these situations, you've got different determinants. So the functional form is different kinds of X's, even different error bounds potentially as well. Even if you fix the levels to be the same, as a form of constraint in how you constrain the algorithm, you can have very, very different functional forms. And of course, what happens then is you run into something called a mental model. So the mental model in this case is represented by this upset citizen who says that, hang on a minute, my wife and I should get the same amount of credit because we have the same financial background. And of course, that means that the mental model says that the only determinant of credit worthiness is this simple thing called my bank account balance, no matter what the gender, no matter who I am, no matter what other data you have about me. And if you don't just use that information, I will be suspicious of you. And I will think that you're making decisions because of gender, race, and other protected variables. So again, the difficulty here is that you can optimize statistically, econometrically, the idea of bias being null, or even maximizing the use of data and maximizing forecasting, and still run into this thing called a mental model that upsets you essentially. Finally, I wanted to touch on very quickly this notion of causality. Causality is of a crucial element to the future of data science, but it's probably one of the least understood and least researched areas. So we can only touch on it here, but we can't really go very far. Really, causation talks about many things, and you can see that here in the presentation. But I really just want to kind of highlight two elements. One is what drives what? What is the functioning element of what I'm doing? As an example to before, what drives someone to repay a credit card bill or not? Clearly, capability might be one. Do they have the money to repay the credit card or not? But two, even if they do have the money, what are the reasons why they might choose not to pay or they might choose to repay? And that means having a mental model. That means having a way of think about how causation happens. Statistically, you can try to establish causation by lagging data. You can say something happens today, therefore something else happens tomorrow, but that does not mean that it is causal. So the classic example in the Book of Why, which I highly recommend that you read, is really around this idea of the rooster and the rising sun. Who listens to who? Does the sun rise because the rooster has crowed? Does the rooster crow because the sun has risen? And in the same kind of causal way, does the sun rise because the rooster crowed yesterday? Again, without understanding what drives what or what is a sunrise mean, you may not be able to differentiate between it in purely statistical sense. I think the final point I want to really touch on is this notion of free will, which starts to feel a little bit uncomfortable when we're talking about forecasting individual actions of agents and individuals of people. And this is really where ethics starts to really take a hold. So the idea of forecasting someone's actions is you take information and data about them and you say something about their future state, future decisions. Are they going to be a criminal? Are they going to buy something? Are they going to, let's say, work really hard at getting to the university course? Typically, we'll take data about them today and we'll project out something else. If our models are very good, we might have really high probability and training, let's say validity, model validity. And in those situations, the question becomes, how much of free will are we leaving this person? If we become very deterministic about our models, we may get very good at understanding whether somebody is going to do something bad in the future. But does that mean that we're in fact limiting their free will or self-actualizations in some ways? And in fact, by, let's say, putting them on a monitoring list for police, by checking up on their house, by taking all these actions because our model tells us that they're likely to commit a crime, are we in fact influencing their behavior? Are we actually influencing who they are and what they do? And so again, this goes back to one of my previous examples about how you can create reality. You can create outcomes by using these algorithms to impact people. And while we don't really care about whether an algorithm knows what I'm going to do in the next microsecond, because that's not really about my free will, that's about a physiological reaction, the need to breathe and so on, I really do worry when it's the next week or the next 2 weeks. So I think really I want to leave you here at this point, and really I've touched on many different topics. We've kind of flown through a whole different range of how we think about biases, how different kinds of biases and sample selection problems can enter a particular experiment, how you can kind of correct for them, but ultimately you think about those kinds of trade-offs you make. And then ultimately some of the biggest societal questions about the mental models you run into, about the notion of free will and the notion of causality. But what I really want to say is that for those of you that are creating or thinking about creating these types of models, you are really entering a generation where algorithms and the interaction between algorithms will be massively pervasive in our society, whether it's the smallest things about consumption or online shopping to the biggest things in terms of whether someone's going to pay their taxes or not. You, as somebody who creates these models, needs to consider the ramifications it has on individuals, on societies, on groups of people to the best of your ability. Clearly, it's very hard to foresee all of the interactions that may happen. But when you're putting together these models and when you're thinking about it, remember that these are manifestations of your will. They are manifestations of what you think the truth is. You are just scaling it across thousands, if not 100,000s, even millions of people in a particular segment of society. So consider that when you're considering doing these models, and keep thinking about this topic as you evolve your technical skills and as you evolve your data science. Thank you very much for listening. This has been Michael Kollo. Take care.